In the previous videos, we discussed interference. This video deals with a single slit diffraction. So you have an obstacle or a slit. Both obstacles and slits behave the same way. So for example, if you had a wave coming in and you had a wall, and a gap in the wall, then the waves are going to come out in that fashion. Now, if instead of a breached wall, you had an obstacle, that obstacle is going to behave the same, give you the same pattern. That's what is not easy to see, but in optics, it's a slit and an obstacle give you the same diffraction pattern. This fact is known as Babinet's principle. The proof of this is rooted in radiation theory, and I won't get into it, but Babinet's principle basically says slit diffraction is the same as obstacle diffraction. A lot of astronomy is really based on Babinet's principle because you can find out details about diffracting objects, which could be planets or even stars. Let's go to the derivation of this. The intensity is what we're looking for. A physics problem is studied in this subject if we are able to predict completely how the intensity looks on a screen a certain distance from the slit. So the distance between the screen and the slit is usually called capital D. And then if you take the midpoint of the slit, the distance from the midpoint anywhere on the screen, so if this is a piece of notepaper or a card, index card, the distance from the center is called Ym, where m is the order of the fringe. In this case, it turns out that if you want to intuitively study this system, it is easier to study how the dark spots form and not how the bright spots form. Now, how do you talk about interference? To talk about dark and bright spots, you need to talk about interference of two sources. That's what we learned in the previous video. But there's only one source, it looks like. There's only one slit. So how can one slit interfere with itself? The technique we're going to be using is subdividing. We're going to take that slit and subdivide it into a certain number of slitlets. So here's what we're going to do. We're going to take the slit and divide it into two parts. Now if you do that, then you can certainly talk about the top part of this interfering with the top part of that. Now remember, since I've divided this into two parts, each one is going to be a over 2. And so, if this angle is theta, and assuming the small angle approximation in all this, that angle will also be theta. And so the path difference we're looking at is this quantity delta there. I'm going to get path difference delta. Now we want destructive interference, so it must be off by a factor of lambda by 2. And so lambda by 2 is what we have for a dark spot. Because remember, if you have two waves and the first wave is offset by half a wavelength from the second wave, that's when you have this crests and the troughs canceling each other out and you end up with a flat line, and that's called destructive interference. So half a wavelength is what we need for dark spot. Let's put what delta is. Delta is a sine this distance sine theta, because this is the right angle. So a over 2 sine theta equals lambda by 2. And if you cancel out the 2's there, I'll get a sine theta equals lambda. That's where the first dark spot will occur in this pattern. Where's the second dark spot going to occur? Well, that will occur when you subdivide this into 4 parts and have the top 2 of each one interfering with the others. So the condition for the second dark spot, delta 2, will also be the same. It's going to be lambda by 2, but this time it's going to be a over 4 sine theta equals lambda over 2 instead of a over 2. You just have to imagine in your mind's eye dividing this up into 4 parts, and the top 2 will interfere and the bottom 2 will interfere to create the destructively to create the dark spot. So if you multiply both sides by 4, I'm going to get a sine theta equals 2 lambda. So we are becoming a little bit wise here. It looks like for the nth dark spot, we have to have a sine theta equals n lambda, where n is some integer. Now it makes sense, at least intuitively, it makes sense to think of the bright spots as occurring in between the dark spots. Now the proper derivation of this requires phasors, and I have done this in my class notes. I won't drag you through phasors in this video, but what I'm most interested in understanding is how this pattern actually looks. So when you go through the phasor derivation, and it's there in one of the pages of my notes, I think page 4 of this week's notes, then what you will end up getting is the bright spots, information about the bright spots and their intensity, and also information about the dark spots. In fact, you'll recover this result as a special case. So first, let's draw the pattern. What are we seeing on the screen some distance away? So I'm turning the screen over, and the pattern is going to be sketched with the intensity on the y-axis as a function of the angle on the x-axis. So clearly, when I have a sine theta equals n lambda, all right, I need to also talk a little bit about the position of the slit. So that would be this quantity d, and assuming small angle is valid, it's not always true, but assuming the small angle approximation is actually valid, I can write tan theta is equal to this quantity y divided by d, and tan theta is approximately equal to sine theta for small angles. So let's write this criterion. So I'll get a times tan theta, which is y over d, equals n lambda, and this tells me that y equals n lambda d upon a. This tells you all the locations of the dark spots on the screen itself for n equals 1, n equals 2, etc. Now this also tells you something interesting about what produces a good diffraction pattern. If you look at a sine theta equals n lambda, you better have at least a few of these thetas as solutions. If you have only one theta as a solution, suppose the only angle I get is something like 90 degrees, that's not going to be good, because then you'll not have a diffraction pattern, you'll just have a big wash. So this actually gives you a good criterion for what constitutes a good pattern. Now, when you say things like good pattern, it's a subjective thing, but in reality, when you go to the lab and the room is dark and you don't see a good pattern, it's really upsetting. So one way to assure a good pattern is to have at least, let's say, 5. Suppose you want 5 bright and dark fringes. What you would do is you'd put n equals 5 there, and you'd solve this equation, sine theta equals 5 lambda over a, and choose that lambda or choose the a so that this has at least a few solutions. Now, let's take some examples. Let's say that A is equal to 5 lambda. That would be the worst situation, because then that gives you just one solution, which is theta equals 90 degrees. That'll be a washout. So it looks like we need A to be a little bit bigger than 5 lambda. Let's say A equals something like 20 lambda. Well, that's actually looking good now. So I get sine theta equals 5 lambda over 20 lambda, which is 1/4. And you actually have a solution for this, and n equals 5, you get 5 fringes within sine theta equals 1/4, which is a small distance. That's not exactly a washout. That's 5 fringes. I should not say it's a washout. It's 5 fringes. Washout would be bigger than that. So suppose I had the worst case scenario would be to use lambda equals a. If I had lambda equal a, the only solution to that equation is n equals 1. And that would be one big hump. That's not going to be any good. So let's move on to discussing the shape of this pattern. Since we know that due to small angles, these are going to occur at regular intervals. So lambda d over a would be the first place where it would disappear, and it would be disappearing on the other side of the central maximum also, so I'll put a negative on that side. And here it's going to be 2 lambda d over a minus 2 lambda d over a, 3 lambda d over a minus 3 lambda d over a, and so on. Now, there cannot be any dark spot here. So what you're having is a huge hump. The central hump is pretty much what diffraction is all about. When you take a telescope and you look at a star, what you're actually seeing is the big diffraction hump of intensity from the star. The second hump is so small it cannot actually be drawn in this same diagram. If the first hump is something like 100 units, the second hump is only going to be 5 units. So you cannot even draw it on the same scale. But I'm breaking scale so as to show you what's going on here. Furthermore, I told you in the derivation that the bright spots can be thought of to be approximately in the middle of the dark spots. That's not true. You should think of this as a sand dune in a desert with wind blowing in this direction. If wind blows in both directions, then what's going to happen is, of course, you're going to get a massive pile up of sand here. And the little ripples that you see will also have a little bit of bias. They'll be more towards the left of the center. That's the true shape of this thing. This curve is known as the sink-squared curve. Very famous mathematical object in intensity studies. So the intensity profile I is proportional to sink-squared of x, and sink x is defined as sine x over x, so it's sine squared x over x squared. Now, when you study calculus, one of the important limits you study in calculus is limit of sine x over x. I believe you spend a lot of time studying that limit, and that limit is equal to 1, and that's why you have this massive hump at x equals 0. The other values of x, this thing will go down pretty rapidly, and you can play around with this function on Wolfram alpha. I strongly encourage you to do that. The minima are precise, but the location of the maxima are only approximate. This function has to be dealt with. The maximum can be found, of course, using the rules of calculus, but the proper way to do it is simply to throw it on a computer and find out where it is. That's the easiest way to do it. So that's the single slit diffraction pattern. In subsequent videos, we will take this and run away with it. We'll also be looking at multiple slits and things like looking through a telescope to find out how close two stars can be for us to look at them as two stars and not one big blob. So that's a big problem in astronomy. For a long time, astronomers thought they were seeing a single star, and then when telescopes got better, they realized that they were not seeing a single star but an entire galaxy of about 400 billion stars. So it's a massive, massive problem in astronomy.